Thank you, guys. And as I think you already figured it out, a lot of talks will be about deep learning because it's one of the major breakthrough. All right, so mainly I will be talking about how you can use MXNet from R. So basically, let's start. So what's MXNet? MXNet is one of the many deep learning framework available right now. It's pretty efficient and flexible. So it's a very lightweight. So basically, it's like a couple of thousand lines of codes, and that's it. You can find the project you can find this project on the GitHub, as well as this presentation code will be available on the GitHub as well. So why I am going to tell you about MXNet? Well, basically, if you take a look on the available packages for Python and R for deep learning with a GPU support, there is not that much of a choice actually for R. Basically, nowadays we have H2O, which will be, and you have a very detailed workshop later this day. Recently, the guys from RStudio, and I think we have somebody from RStudio today, hi Jeff, and basically he might enlighten me, because that's something I learned like recently. They published the R TensorFlow package, which supports TensorFlow, which is great, and I will definitely have a look into it. And the MXNet, that's just a free packages available. That's all you can do deep learning using R. Well, and because of it, I'm thinking it's a good idea, you know. I always felt myself like, you know, like limited because I wasn't able to do any deep learning stuff in R. And that's actually, to me, honestly, it was like one of the main reasons why I switched to Python. You know, so I'm able to use like an all deep learning package available. Nowadays, we can use MXNet, and basically, what I'm going to show you is some sort of the example how it can be done, but instead of using like images data, I am going to use the data set from the financial sector, which is I thought will be kind of more applicable to audience, and it's more fun to do actually compared like to like a standard stuff with the cats and dogs. Sorry, Bill, about that. I hope you can hear me. And so the pipeline for our presentation will be quite simple. So first of all, we need to get the data, process the data, and train some neural net or nets if you have time on using this data set. Well, I use a public available data set. It's available on UCI machine learning repository, and it's I think it's from Asian bank. And what you have to do, you have to predict the next month credit line default for clients for this bank. The dataset has a mixed types of the features. You have a 3 categorical features and 20 numeric. And one of the main difficulties of using deep learning on this kind of structured data is that you have to normalize your data before you can really apply the neural nets to it. Like you have to somehow encode your categories. You somehow have to normalize your numeric features, so the distribution will be like around the 0 and the mean, the standard deviation equal to 1, or as close to that as possible. Which can be a kind of time-consuming process. So in order to avoid that, there is a very neat package available for R, which called and it's all about the second part of the process data, which called VTreat. And basically, that's a very interesting data frame processor. And in a nutshell, it's a very, you can treat it as a black box most of the time. So basically, you put the data inside, and you get a really normalized data which can be applied, and you can use any machine learning to this data like right away. So they try to look for all common cases, like dealing with non-available data, like missing data, real categories values, like novel categories values, etc., extreme values reduction, and all this stuff. So in short, it's a very awesome package, and the link is again available in the presentation. And so basically, you can learn a lot about it. And this package in particular has you can have it's worth to have a talk on its own. And yeah, so basically, after applying VTreat, we can actually apply any machine learning neural network model to the data like right away. without thinking about how we can, it will be already like normalized and ready for use. So yeah, for this particular data set, there is not much of the transformation we can do. We just do categorical encoding, changing the data to categorical values because it's integer encoded. We remove ID value. Of course, we have to split the data set before we are going to, to apply any machine learning algorithm. So we have our validation set available. And that's a VTreat. So it's just 6 lines of code, and we already prepare our data set for using a machine learning algorithm. Now to MXNet. So basically, if you are a Windows user or a Mac user, it's very easy to install it with a CPU support. This GPU support is not that easy, and I'm not sure it can be done. I mean, I never done it by myself using the Windows or Mac machine. It's usually you prefer to use like Linux machine for that. So yeah, and actually, the easiest way to train MXNet actually is to use an MX.MLP function, which is a kind of wrapper and creates the standard multi-line perceptron for you. So it works almost in the same fashion as you work with the H2O deep learning model. So you just pass the data set, the target variable. You can identify how many neurons per layer you're going to have. You can define what kind of activation function you're going to use, how many outputs you have, what type of output activation you have. Like you have instead of in case of binary classification, you're using just logistic. If it's like an regression, you can use RMSE and softmax out of the box. You can define optimizer, and MXNet has plenty of them. So basically, all like a new one optimizers can be used, and vanilla SGD as well. So it's up to you. You can pass how many epochs are you going to train your model for, what the batch size, learning rate, and all this usual stuff. You also pass what kind of device to use, and usually it's used mx.cpu by default. In case if you have a GPU or like several GPUs, as I was lucky to have, you can specify that you're going to use the GPU and the device ID. It's a number from 0 to n. You also can pass an evaluation metric. And unfortunately, in the R package, MXNet does not support a lot of them. And basically, I have to implement my own MX.metric multiple log loss metric, just to be able, because the default metric is accuracy, and I don't think it's very applicable for classification task and for neural nets in particular. So, and after that, you're done actually. So you just need to, here's some code snippet how I end up implementing the log loss. And here, basically, after running the MX.MLP function, you're done. You already have a trained model, and you can run a prediction out of it. And just to make things even funnier, I run the random forest with the 500 trees on the same data set and the same data split, just to have like a baseline model. And it turns out like this pretty simple neural net, multi-layer perceptron, do pretty good actually on the same data. All right, but yeah, that's something. MX.MLP is a quite interesting function, and so it makes the creation of a multi-layer perceptron quite convenient for you. But you trade in the flexibility for convenience actually. So it's not that flexible. Basically, for example, for this function, you can introduce the dropout if you like to, but only for the last layer. But in some cases, it could be a good idea to use a drop layer for the first layer of your network, especially if you have like a kind of noisy data. So you'll help your neural net not to overfit. All right. So of course, there is a way to build your own neural net using MXNet. And basically, what you do, you think about the neural nets as a directed graph. So basically, you have blocks. Let's say like your fully connected layer. It's just a block on your graph. You have an activation function, which is another block, and you just connect them to each other. Then you have another fully connected network. So basically, what this code does, it does the same. It creates very much the same MLP as we did with the MX.MLP function, but in the like manually. So you can do a lot of funny stuff here actually. So after you created this graph, you can train it using a feedforward.create function, which you pass pretty the same parameters actually which you pass for MX.MLP function. So there is also a neat functionality in the MXNet. I'm not sure it will be very visible here. Yeah, it won't be. So, but basically you can visualize your network. And the red bricks, it's our fully connected layers. The yellow one is an activation layer. And the pink one is the endpoint. It's an output. So it's an extremely helpful function because, you know, if you build your network, your graph by your hands, you just need to be sure you connected all and each layer like in the right fashion, in the right order, because otherwise the model will produce something not expected at all. So, and as I mentioned, if you manually create this type of graph, you can do a lot of different stuff, and you can put in different blocks, and which is more important because, you know, deep learning is all about finding the right architecture for your data set. That's how all these competitions won actually in the last couple of years. They just introduce not just some fancy optimizer, they just introduce some different architecture. So instead of creating features nowadays for deep learning, you create the architecture, different architectures. So, and basically one of the strong thing about using this graph approach, you can connect different layers, not in the straightforward fashion, but anyhow you like actually. So it's yeah, just release your creativity and do whatever you want. For example, for this data set, I decided to create additional network to slightly improve the results. And for example, I added a dropout layer right after the input layer, which is variable data, with a quite small probability, just to help the model to learn something useful. And usually, if you have a quite noisy data, it helps. I always want to try a batch normalization on using MLP, so I did that. And as well, I just get some trick from residual nets, and I just connected the layers in some not the straightforward fashion, I would say. So basically, if we visualize our network, now we have, I'm sorry, it's barely visible here, unfortunately. All right, so what you can see here, I use additional connections between different layers. So the network can learn some additional, let's say, residuals, but I wouldn't use that word actually because it's not quite the right. And by using this kind of a model, you can get a pretty good results and beat the random forest. But again, it's more like because I use a random forest as a baseline model, so I didn't do any fine tuning, so it might be not the right. Because the biggest thing, based on my previous experience from practical point of view and from Kaggle competitions, it's very hard to beat the tree-based models on the structured data sets. But I still believe it's possible, and it might be just additional inventions will be done in the next couple of years. So again, this code is available on the GitHub, as well as this presentation. So there is a R code there and the IPython notebook with R kernel. So feel free to use it anytime you like. So, to summarize my presentation, what I'm trying to tell here, it's really possible to build a very interesting deep learning and neural nets using the R. So if you're an R user and an R programmer, feel free to use it. I'm encouraging you to use it, and it's quite helpful and fancy. And if you use a VTreat for your data preparation step and your data cleaning process, it's a good idea actually. So VTreat plus deep learning can bring you very interesting insights and findings. That's pretty it.
Is this available in Python also, or just in R?
MXNet can be used from Python as well. My code available on R. Well, because again, my point was to introduce how you can do it on R. But yeah, it can be easily switched to Python as well.
Can I still use the CPU if I don't have access to a GPU.
Yes, exactly.
It'll take a little bit
And for
more
this
time.
particular data set, it's a very small data, so you won't spend a lot of
Okay.
time actually. You can use it, yeah, definitely.
And the code is, I can run it as soon as I download it from GitHub?
Yeah, sure,
Okay.
sure. As well as a data set. I think I put the data set as well here, there as well, because it's a very small data set. So technically speaking, you know, it's kind of a trick, because usually you don't use the neural nets for the small data, because it doesn't make sense.
No, but it helps to get into
Exactly. That's the whole point. Yeah.
you can reproduce it and learn from it.
Yes, yes.
Hi, what was the purpose or the use case related to the credit card client.csv kind of data? Were you trying to do some kind of a fraud detection or a credit card application? Is that the purpose of you showing that data?
It's a prediction of the defaults for the credit card users. So you're trying to predict, are they going to pay for the credit in the next month? So, and main reason was, you know, I just trying to find some what I would say non-standard data set for neural net, and I ended up using this financial data set because it was quite new. I never tried it before, so you know, it's like.
Okay, so what's really happened to the categorical variables or missing value? You mentioned a package would take care of it, but what does that mean exactly?
Yeah, there is a lot of vignettes for this package in particular, so you can go to the GitHub and read it by yourself. But basically what it can do two things. It can one-hot encode it for you, or it can transform using the output. So there is a usual technique in the data science. So then you replace your categories using the mean outcome value, or expected, let's say. In terms of the binary classification, you might think of it as a probability of seeing the default for this particular category, for example. And it handles the rare categories as well, so it won't overfit. So it's yeah, so it does pretty good job. Well, of course, you have to. You might be right. But when I say you can blindly throw the data set inside, it's not a very good approach at all. So you have to learn from the data for yourself.
So you said you could use multiple GPUs. How well does it hide the overhead of communication between those GPUs?
These GPUs supposed to be on the same machine. So
only on the same machine.
Yeah, I'm not sure it's possible in the in the cluster fashion.
Okay. Yeah.
It's something. I mean, especially for MLP, you can do that. I mean, but for convolutional neural nets, for example, no.
For those of us who are just learning about H2O, can you describe how MXNet fits into the overall H2O product
That
framework?
will be something that Arnold presented later this day, actually. There will be a workshop, like a 1.5 hour workshop. But basically, what in a nutshell, you just create the model using the MXNet. You import the model like in some format, and the H2O can consume the description of the model inside itself. So that's.
How this MX library compares to other frameworks like TensorFlow or the H2O deep learning models in terms of time and accuracy?
That's a very interesting question, actually, in terms of time and accuracy. By saying time, you mean the time to train or time to learn?
Yeah. Training time.
Training time. Well, basically, it's pretty. To me, it's more about how the convenience of usage of the framework itself. Because from perspective of performance and the calculation time, let's say training time, it's fairly the same. The code is pretty optimized for all of these frameworks. So I still thinking it's more about is it convenient? I mean, are you able to express what you really want to express using this particular framework and using this particular language? And from this term, I mean, I think MXNet lacks a couple of features you can use from TensorFlow, and yeah, so but it's fairly good.
Thank you so much.
Thank you.
Thank you, Dmitry.